exciting to actually see closed captions. That is part of what I'm going to be talking about today. Closed captions is probably one of the use cases for speech recognition that you're probably familiar with because you've probably used them in some sort of applications, or at least have seen them live. So we're going to talk today about ASR, TTS, and adding voice to applications. We're going to talk about both. ASR is basically speech recognition. TTS is basically speech synthesis. Hi, I'm Caterina. I also forgot to include a title page about myself. In fact, this is what someone reminded me to do at lunch today. I was like talking about what my talk was going to be, and I was showing them, and they were like, "Are you going to introduce yourself at some point?" So I had to put this together at lunchtime. So I'm Caterina. I work with web technologies as well as voice technologies, and then I also teach about these topics. I work at Portland State University. I also do consulting work for working for various tech companies. So the way I have this structured today is sort of just like kind of like a brief introduction, kind of making like a case for using voice, specifically regarding kind of like the ecosystem and where things are headed. I wanted to also talk about, again, like ASR and TTS, just to kind of understand behind the scenes what's happening at every point. Obviously, like one of those is something that's fairly complicated, and so we're going to talk about it, but really talk about it at a high level. I also thought it would be like important to talk about limitations. Speech recognition is really exciting. There's a lot that we have figured out, but then there's also like really problematic issues, and I think it's just important to take a few moments to discuss those. And then just like we can go through some code samples, specifically using the Web Speech API, which is just a free API that's really easy to use within the browser. Obviously, there's more APIs beyond that, free as well as paid, but that one is a really easy one to get started with. All right, so why voice? I mean, the entire ecosystem, the entire voice assistance and voice in general ecosystem is just growing quite a bit. And so these are some numbers related to that. I also have the sources, but I guess it's just getting a little bit cut off. But I can send you the link to this, and then you can, if you want to take a look through where some of this information comes from, it's linked at the bottom. So 4.2 billion digital voice assistants worldwide. Again, it's just, we're seeing a lot of, this really depends by country. Obviously in the US, we're seeing a lot of hesitation due to security issues, but that's not actually the case all around the world. There are some countries where this is more widely adopted. But even in the US, obviously a lot of people do use their voice assistants and just have learned to use voice in general to operate different devices. Voice assistant users conduct 3.1 billion voice searches each month. Voice searches is, again, going to be like the most popular thing that most people do. 80.5% of respondents aged 18 to 29 have used a voice assistant on their smartphone at least once. Obviously, that's a really low bar, but again, just lots of adoption for, like a newer generation. So that's always good to see. Beyond that, I would say that voice in general makes applications more accessible because in general, people are going to be able to figure out a technology more readily with voice than they might through reading. And the reason why I say that, just thinking around the world, the specific data around literacy is that an estimated 181 million people over the age of 15 have yet to learn how to read. And so as we think about like how we're going to open up the web to the rest of the world, like obviously, I mean, to like everyone in the entire planet, that includes obviously like people in the US, but like all over the world as well, voice is just going to be the more accessible option. So it's just kind of like some data. Obviously, like lots of improvement, but what we see over here, that's like the 780 million people. So still a huge number. And global literacy rates, I thought this was interesting, so I added this in here. 90% for men, 82.7% for women. So this takes us to ASR. ASR stands for automatic speech recognition, and this is when we talk about speech recognition and speech recognition systems, we typically talk about ASR. Now, at a high level, this is sort of like what happens as part of this process. We sort of, speech recognition is essentially speech has to get transformed into text. And so there's three main steps. The first one is digital or feature extraction, and this is done with like digital signal processing. And then the two pieces that are huge in terms of NLP are going to be the phoneme identification, which uses an acoustic model, and word identification, which uses a language model. And these acoustic model and language models, this is where so many people are working. There's just an incredible amount of work being done because this is what needs to improve for speech recognition to get even better than it is today. So feature extraction in general is essentially like when we start with raw data, especially when it comes to speech. Speech is our raw data, but speech isn't something that a computer can use, and so we have to transform that into something that can be used, that an algorithm is going to be able to use as its input, and so that's going to be some sort of like analog to digital transformation. And so how do we do that? Again, I mean, this is part of like digital signal processing. Like this is absolutely not something that I'm very familiar with, but at a really high level, we're essentially using a microphone. Our voice is really just vibrations, and that microphone takes those vibrations in, and it's able to transform them into something digital. Now that digital transformation is going to be the spectrogram, which is something that you've probably seen. But a spectrogram is going to show us the different frequencies of our voice. And so it looks something like this. And in here, when you say a specific sentence, a microphone is going to take that in and produce something like this. And this is something that that we can then take and actually like work with. Now, obviously, like spectrograms are huge because as we speak, we've got a lot of this. But what they're divided into is going to be specific phonemes. And so like if you were to sort of like cut this up into different columns, what you would have is individual phonemes. And a phoneme is the smallest unit of sound that has sort of any meaning, which is not exactly the same as sort of like a letter, but this is a little bit of how they translate. So this just has a lot of color, and this is how you will usually see it. But if you sort of like think through those images at the top also having a lot of color, they're going to be essentially the same. But our language is going to be divided into these different phonemes. And so with our phonemes, what we're going to do is we're going to map them to specific letters. Well, in between there's graphemes, there's also like lexemes, but that's for like a much longer discussion on all of this stuff. But for example, when we have the S phoneme, that is something that's going to translate to the letter S. But then down here, we have these two O's, which the sound associated with that is going to be, like spoon, the oo sound. So our phoneme in that case is going to be that oo sound. And so it doesn't translate automatically to letters, but we have the individual phonemes. And so once we have that spectrogram, that's when we can start identifying all the different phonemes, and then we can try to figure out what phoneme comes after another. And so in this feature, we take in features, we output different entire words based on their phonemes. So again, phoneme is the smallest phonetic unit in language that is capable of conveying a distinct meaning. Now the step is going to use an acoustic model, and acoustic models there's various different acoustic models out there. And what they are is essentially pronunciations of various different sentences, various different words, everything sort of put together. That's going to allow us, in this step, using an acoustic model, we're going to be able to figure out when we have the letters, when we have something on a spectrogram, like the S, the P, the U, and the N sound, is that going to be spun, or is that going to be spoon? So again, based on, this step is also going to use hidden Markov models most often. It's a fairly complicated algorithm to essentially try to figure out what works best. Because obviously we're going to have, our different phonemes can be specific words, but if, maybe it's spun, maybe it's spoon, but that's really going to depend on what comes after. And so that's, there's sort of an algorithm that's going to go back and forth and try to figure out what makes more sense. And so even as what you're seeing over here is sort of the final, is sort of, I guess, the final transcript in a lot of ways. But when you run speech recognition algorithms, a lot of times what you're going to see is they're going to have something where, there's going to be a specific word, and then it's not going to make sense, so they go back and change it. But obviously, this is a full product. That's probably a paid product, which is why it works significantly better than just, just using specific APIs to put this stuff together. And so that's what happens as part of the acoustic models is this. It's just always trying to figure out, okay, these are the phonemes. What do these phonemes put together? Is it this word or is it this other word? And so part of how this will happen is, various variations in prosody. Prosody is going to be intonation, stress, and rhythm. So for example, we have spoon versus spun. We have different emphasis in how we're kind of pronouncing that U sound. And so part of that is how it's going to make those decisions. Sometimes it's going to get it right, sometimes it's not going to get it right. But that's fine because we have another step after this. So even if we haven't necessarily figured out sort of the right way to put these words together and put these phrases together, the last step is going to be the word identification. And this is where we're going to be using a language model. And in fact, I think I needed to go over this. So in terms of the acoustic model, I wanted to mention this. So these are some of the top corpora that are being used out there. Some of these are free, some of these are paid. Many of these get built in-house, and so we don't have any sort of sometimes we know what they are, sometimes we don't really know what they are. The most popular one that tends to get used quite often is the TIMIT one. How do these get put together? Various different ways. The initial corpora for this stuff was actually just people calling different call centers and the voices between whoever was answering and you would get recorded, and that's how some of the initial corpora got put together. Some of the there's another really popular one that comes from audiobooks. So that's why, because it's actually like really difficult to put this stuff together, and it's really difficult to get all like voices that you need to get. It's really difficult to get all different accents and dialects that you want to get. And so, we kind of like end up with some of these. Some of these are going to be free, but again, Timid is probably going to be the most popular one. It's recordings of 630 speakers of 8 major dialects of American English, each reading 10 phonetically rich sentences. But as I mentioned before, like this one is an open sourced one, LibreSpeech, so you can just use it if you wanted to. You don't actually like have to pay for it. You can just kind of download it. But it comes from audiobooks and from public domain audiobooks. And so the issue there is that people who record audiobooks typically do a really good job of speaking, tend to not have accents or like dialects or like speech impediments. And so, you kind of end up with these acoustic, these corporas that are being used as part of the acoustic model that don't necessarily provide, all the richness of the language that they should. Okay, so let's go back here. Sorry, that was a little bit out of order. I just decided to change it up a little bit. But now that we've gone through the acoustic model, the next thing we do is word identification. This uses a language model. What happens with the language model? Well, that's where we can figure out, like, okay, do these words really, does it make sense for these words to come together, or do we need to still loop through and figure out like a better sentence? Now, I have a demo at the end, and if you take a look at that demo, you are going to see, again, this is kind of like the finished product of speech recognition. But if you take a look at what's happening as it detects language, you're going to see it's going to put the wrong word up there, and then if you take a look at the object inside, you're going to see that its confidence is maybe like 50%. And so as we go through the language model, then we can go back and be like, okay, that doesn't really make sense. We have to keep going. Maybe there's like a better, there's like a sentence structure that works best. So this uses a language model comprised of words in a language and their pronunciation, and this step provides context to distinguish between words and phrases that sound familiar. Now, in terms of language models, you may have heard of these. Some of, probably one of the most popular ones out there, BERT. It's been used in almost everything. GPT-2 and GPT-3, which came out really more recently. These are also just very common ones. A lot of people are working on this stuff. Again, like the better that we can get these acoustic models and the better that we can get these language models, the more speech recognition is going to improve. So this is sort of just kind of like a review, feature extraction, phoneme identification, word identification, and then what we get at the end is going to be text, a bunch of phrases and sentences that hopefully make sense, that are going to look something like what we have over there. Now, the flip side of this is going to be speech synthesis, where we don't take in speech from the user, we take in text from probably our application, and we deliver speech to the user. So this is, a lot of times it's going to be referred to as TTS, text-to-speech, but it is also known as speech synthesis. Now, everything that happens here is converting text to SSML. SSML is going to be speech synthesis markup language. This is what's going to allow us to specify sentence structure, pronunciation, volume, pitch. It's a markup language, so all that we really do is we take the text and we add different markup to let as we get to the wavelength production form, to essentially like figure out all of those different pieces. Oh, sorry about that. So at each step, structure analysis, this is just sort of like putting everything into like paragraphs, into sentences, into taking that text and sort of like adding some initial markup to it. The text normalization part takes a bit of a long time. This is something that we just know. When we read a specific sentence, we're going to know how to read different pieces of it, but a computer doesn't know, and so we have to specify those pieces. Text to phoneme is really a pronunciation dictionary. Things are going to be pronounced differently depending on the phonetic alphabet that we want to use, but also just in general, we might pronounce something, you know, tomato, tomato, so those sort of things. Prosody analysis, this is like tone, volume, pitch, all of that stuff, and then wavelength formation. And so just kind of taking a look at just like an example, starting with a sentence like Dr. Smith lives at 162 Portland Drive in Oregon. He weighs 162 pounds. He plays bass guitar. So we have like maybe a paragraph. The P is a paragraph. The S is a sentence. So we're just kind of like adding that initial structure. The text normalization is several different markup tags to add more information. So when you and I read this stuff, obviously like Dr. Smith means doctor, but we have to make that clear to a computer. And so the specific tag for this is going to be sub, so sub alias doctor versus sub alias drive for Portland Drive. And then the other piece of this is if you are going to have abbreviations, if you are going to have anything else that isn't clear, that's when it needs to sort of like be clarified. So LBS, it's actually pounds. The text to phoneme, so again, we'd be adding like phoneme to a lot of pieces here, but I didn't want to make this like too complicated. But in here, we can specify the alphabet. The IPA is the International Phonetic Alphabet. It's going to be the most popular one. Every now and again, you know, there might be other ones, but in terms of the one that's going to be most closely associated with all this is going to be the IPA. And so we can specify specific pronunciation. If we wanted to sort of like do another pronunciation, technically we could as well, but that would have to be specified in terms of like phonetics. So like how should bass be pronounced? And supposedly that's how phonetically it is. So prosody is, you know, the way we talk. Oftentimes we don't think about it, but sometimes we have like a higher pitch, sometimes we have a lower pitch, sometimes we talk faster, slower. So that's sort of the things that, you know, we can specifically add. We can add this for all sentences. We can also add this for no sentences. But in terms of markup, we're looking at the prosody tag. And so, for example, we can specify volume soft, but, you know, you can do like medium, loud, other things. Pitch as well is something that you can specify. So those are the pieces of it. And then wavelength production, this is kind of like where you put it all together. You have like everything you have, and then you specify the speak tag as well as the voice. The voice is where you can decide what type of voice you end up using. Now, in terms of like speech synthesis APIs, you're going to get a certain amount of options. So sometimes you will see, you know, NUS, but sometimes you might see NUK or NCA, and then different voices. So you've probably seen this if you've worked, like for example, on your GPS in your car, you can typically change the voices. It's just, but it's going to be one of the options that your specific speech synthesis API is going to give you as an option. And so that's essentially speech synthesis. Now, I do want to go back and talk a little bit in terms of limitations associated with speech synthesis. We've touched upon it for a few moments, but I think it's just something that obviously we want to be aware of. Now, this is a study that made the news when it came out. This was 2020. This is a study from Stanford University, and they examined 5 different ASR systems. These were from some of the biggest companies in the tech industry, Amazon, Apple, Google, IBM, Microsoft. And they transcribed specific interviews with 42 white speakers, 73 black speakers. So the word error rate was 0.35 for black speakers, 0.19 for white speakers. A lower number is better. The word error rate is all of the total number. You take the additions, so any word that was added that shouldn't have been there, the subtractions, anything that should have been there but wasn't. And everything that was wrong, that was there, but it wasn't the correct thing, and you divide it by the total number of words. And so that's kind of how it turned out. This is just from that study. And so as you can see, just across the board, there's just a lot of work to still be done. Now, the reason why did this happen? In that study, they talk about the acoustic model. And they talk about, again, the specific corpora that was being used. And that specific corporas don't necessarily have all the dialects that they should potentially have. And so many different voices are getting transcribed incorrectly as a result. But then there's also a typical speech. So for example, when you think of any sort of speech that is going to be more difficult to be interpreted, this can be obviously by a computer, but this can also be by you and I. So this is going to be various different speech impediments, stutters, just things that may have left someone with sort of more difficulty in speaking. Again, we just don't have those specific voice samples. And so when someone with some sort of speech impairment is going to try to speak, it's probably not going to work particularly well. And obviously accents and dialects. So really quickly, just kind of the difference. An accent describes how someone pronounces words. A dialect is also how someone pronounces words, as well as general vocabulary and grammar that might be different. And so thinking of dialects within the US, people speak slightly differently, but then they also use different words, like soda, pop, sort of thing. So this is sort of a study where we have some dialects, but then we also have accents, and we're kind of looking at, accuracy. Overall accuracy was 83%, so that's this line. What was higher than that versus what was lower? And again, we're looking at 2 different devices, and so those are going to be 2 different ASR systems, one from Google, one from Amazon. And as we can see, it's not necessarily the same dialect that is going to work best for both, and it's not necessarily the same accent that is going to be worse for both. And so this is sort of the same thing, just kind of another way to represent that. This is sort of another study. 2 teams of researchers from the Washington Post tested thousands of voice commands dictated by more than 100 people across 20 cities. Google and Amazon speakers were 30% less likely to understand non-American accents than those of native-born users. This is probably something that isn't much of a surprise. I think that if you have seen a non-native speaker try to use I don't know, something like speech recognition in their car. It just, oftentimes it doesn't go well. This is a video, and I don't know if I'm going to be able to play it. It's actually on this website. Yeah, maybe we'll come back to it at the end. It's just one of the tests, and nothing actually works for this person. It's just a little bit unfortunate. But the issue with this, sometimes we might, play with our phone and try to ask our assistant one thing and it understands something else, and it's really funny, and we're just kind of like laughing and, no big deal. But as we're seeing, a lot of this technology is being used as part of technology, and people's lives sort of end up depending on this stuff. So this is an example. This is about an Irish woman who failed a spoken English proficiency test while trying to immigrate to Australia. Obviously, you might be like, well, these things are going to happen, but I think what's sort of really telling is what the companies who put out this information do have to say about this stuff. So in this case, the test was issued by Pearson. I think it's a company that does a lot of testing. The company has categorically denied that there's anything wrong with its computer-based test. Obviously, there is something wrong. The issue that is wrong is it's not able to understand. It wasn't trained on accents. It can't recognize it, and it's taking someone whose English proficiency is good and saying that it isn't. And obviously, for this person, this would probably impact their immigration status, so likely a pretty big deal. Hiring practices as well. There's this company HireVue, and what they're doing, what their product is it interviews candidates before the HR person ever talks to them, so it says yes or no. And again, the CEO, you can read the entire article if you would like, but several journalists tried it. It didn't go very well for them. The CEO responded saying that the algorithm is always right. It would be a yes or a no. I feel like this sentence in general, the algorithm is always right, is just fundamentally wrong. But we're getting to a point where people are seeing this stuff and really not thinking through it. So I do think that it's important to kind of come back and think about this and think about, as you're building products, what does that mean for the people that are getting just having their lives impacted by this technology. And then the last one, car technologies. Car makers have acknowledged that many women seem to have issues with car technology. And so there's this quote over here from the VP of a voice technology auto supplier for ATX Group. Many issues with women's voices could be fixed if female drivers were willing to sit through lengthy training. This is actually a quote. I didn't change this. You think I changed it, but I didn't. Women could be taught to speak louder and direct their voices toward the microphone. There's also studies about this, speech recognition systems, understanding genders differently. Part of that is, pitch. Part of that is volume. But again, this is probably not the way that we want to go about this. And so I really just wanted to take a few moments to kind of highlight all of this stuff. There's more that needs to happen in terms of voice technology, in terms of the acoustic and language models, but also as we start using this technology, it's really cool to build, to just quickly start building something. And to see, people being able to use it. But I think it's also important to recognize that sometimes, does that, what we build, does that mean that everyone can use it? Does that mean that we've thought about who can and can't use it? And yeah. So this takes us to our last part. And these are just a few code samples. Again, this is the Web Speech API. I really like it. I think it's one of the easiest ones to get started with. Obviously, Google Cloud, AWS also offer solutions for this. There is something that's part of Google Cloud Services that I've included that I think is also really cool. But the thing about the Web Speech API is it's available in your browser. If you want to start working with this stuff, you can. If you want to start using both like speech synthesis, putting together various different web applications and also various like Chrome extensions or things around that, you can. It's pretty straightforward in terms of like getting started. Okay, so in here, this is kind of like a list of some speech recognition software. There's many more. They will all offer some sort of like free tier, especially like in terms of like if you're a student or still learning, you can usually like try it out at first. And then there's like some free ASR tools as well that you can start to look into. Okay, so speech synthesis, and I do just really quickly want to okay, actually, let's go here first. Okay, so in terms of speech synthesis, we've got, this has gotten a lot better over the years. I started using the Web Speech API. So the Web Speech API includes the Web Speech Synthesis API and the Web Speech Recognition API. This has gotten a lot better. Speech synthesis is also significantly easier to use. So as you can see, most browsers at this point, you can use this with. And speech recognition is not quite as good, but you actually can, you can use it in Chrome, you can use it in Safari, you can also use it in Firefox, but you have to manually change your settings to be able to use it. And so I think that's what the little flag is here. So you are a little bit limited in terms of like which browsers you can use, but I think for most people, Chrome, Firefox, Safari are going to be really popular ones to use. So in terms of getting started with it, are you all web developers? Are you all pretty familiar with web development? Okay, yeah. So it seems like a lot of hands in the air. So this is JavaScript. You are using a browser API, so it's probably going to always be easier to, yeah. Oh yeah, sorry about that. Yeah, so these are, yeah. And you can also like go in here, and in fact, I can make this a little bit bigger. So it sort of like tells you specifically partial support refers to like some attributes missing, but really pretty much everything is there in terms of Chrome. And for the most part, you're only looking, at like the latest, because obviously, some people might still be using Chrome 4 to 24, but most people have probably upgraded at this point. You would hope so. And then if they haven't, well, that just means that you want to check that their specific browser version has this. If it doesn't, you just let them know that that feature is not going to work. So speech synthesis, we have the speech synthesis utterance object. That's kind of like how we just sort of like pass any sort of utterance to it, and that's sort of like all there is to it. It's actually like incredibly easy. Now there are a lot of things that we can specify. So we can, well, for starters, the text, that is going to be the string that is going to be spoken. But we can also specify the language. There is the speech synthesis utterance is going to have a get languages method. And that's going to give you all the different options in terms of languages that you can use. So you can change that language. If you don't set it up by default, I think it is going to go with like where your browser is located. So I think for a lot of us, it's going to be the NUS, but obviously like there typically are going to be options usually for like NUK and different countries that use English. You can specify various different things. So I just put those 3 inside of the settings, but there's a few more that you can change. I think those are going to be some of the ones that get updated most often. And then you just do speech synthesis speak. And then your whatever you have. And so, again, you can set this up to happen on a specific, you can have an event listener. So if someone, I don't know, navigates to a page or navigates to the nav bar, you can have the event listener listening and then firing off some sort of function where this takes place. You can also have something that happens on utterance on end. So pretty straightforward. You can also check to see, so Windows Speech Synthesis is going to let you know if you do have that speech synthesis object. But again, when we were taking a look at can I use, most of that, most browsers do have speech synthesis for the web speech APIs. And so you can just you can fetch some sort of element from the DOM, you can sort of take the value of that element, and then you can so you can have someone fill out a form, and then you can just be like, you filled out all this information in your form, for example. So there's various different things that you can do. It's all pretty straightforward. Speech recognition is going to be, there's a little bit more that needs to happen because you're going to need to parse the results. Once you parse the results, it's going to give you, various different words, but it's not actually going to put sentences together for you. If you use some sort of paid product, you are going to get full sentences with capitalizations and commas and punctualization. So in terms of speech recognition, it's much more important to sort of start by checking whether you have that speech recognition object, so window.speech recognition. And then WebKit speech recognition, again, that's just going to check your specific rendering engine. In terms of how to use this, it's the same as with speech synthesis and the utterances. You use the speech recognition object. You have various different settings that you can set. You are going to need to be more careful there. The interim results, that's going to tell you everything that happens. So, for example, you say hello world. You're going to start with an H and an HE and an HEL. So those are going to be the interim results, or you can just look at final results. So you are going to put together you are going to start the recognition and then you are going to stop it. You are going to need both of those. So that's going to be the stop method and the start method. I put the stop method on this page because it just fit better. But the start speech recognition, again, you're just adding an event listener. You're listening for it's really an object, and you're just listening for when you do have a result. And as soon as you have a result, you can start sort of parsing all the data within it. Various different ways to kind of parse. You're just going to have all these different objects, and what you want to do is you want to get to results and results 0, and then results.transcript. That's inside of your object where all of this information is going to be. And those are going to be specific words. And then I guess you're just joining them. And what you're going to end up is going to be all these different words together. I did put to... okay. I think I'm not able to click on this just because it is within a PDF, although I'm not actually sure why. Oh, here we go. So this is, it's just sort of like an example, kind of everything we talked about, but you can actually run it. It's just like a basic HTML and a basic JavaScript file. And you can sort of like run through everything. You can also just kind of like make changes. So you can take a look at that if you would like to. So I'm going to open it in a new file, and then I'm going to go back here. Okay. I don't actually have, I think there's only like one more slide. Oh, shoot. I thought I was going to be way under time. But that's fine. We don't have to take a look at this. Dialogflow is something that I love to use as part of the Google Cloud. You put together this agent. Putting together an agent is putting together an interaction model and a fulfillment. It's super straightforward to use. You build most of it. You can build most of it within the UI. It obviously really helps in terms of the fulfillment to put together like more logic using Node.js, using Python, whichever you're more used to. But it's great because it then creates this, this sort of agent that you can add within any sort of website. This just kind of looks like a messenger app, but actually this all works with voice. And so it's just like a really nice thing to kind of add to a website. It allows, you can pretty quickly set up, like the main different steps in your website. You can actually have kind of like a messenger slash voice assistant there to kind of like help with those specific issues within the site. So I love using this. I teach Dialogflow, and I think it's super useful. Okay, questions? Yes. It depends. Are you asking specifically about the web speech API? I think that's a really good question. I actually don't know, but I think it's mostly English. Yeah.
Let me add like a little because I'm pretty broad, like Google doesn't understand me the language, so what can I do to contribute to it?
Yeah. So the web speech API, there are lots of contributors that add specifically to the MDN pages. If you go on the MDN pages at the bottom, all their different contributors are listed. I know it's an open source project, but I don't like, it hasn't been very visible. One project that has been more visible is Mozilla Voice, Open Voice, and it's one of the things that Mozilla is doing to, try to put together like better acoustic models. So what they're doing is they're allowing people to record their voices and add them to this like Mozilla Voice project, and it's actually like pretty cool. I think I don't have any information about this here. Mozilla, that's not going to give me what I want. Yeah, Common Voice, and you can record your voice saying various different things. If you go in here, you can take a look at all the different. They have many languages that are sort of. There are just a lot of different languages, and you can get more information in terms of like the number of speakers, the hours. Now, this is a community project, so you record your voice. Someone has to approve it. So it's not just you saying like, everything is correct. Someone does look through it. So, I mean, that could be one way to kind of like contribute. Again, it just really depends. There's also, Google is doing this Project Euphonia, which is really about recording atypical speech. That is also like open, but not as open as Common Voice. Again, these corpora, they're being recorded, but sometimes it's just happening in-house. And we don't necessarily have like any way to change the decisions being made about it. Yeah.
In the breakdown, you had the words themselves, the individual sounds. Are all of them starting at that level? So, for example, if someone were talking and I were listening to them speak, I would be using the context in which they were saying what they were saying, as well as a full sentence to get an idea. But if I took it word for word and down to the individual sounds, I get a better understanding of what dialect they're speaking based on a larger sample size than the individual words. But if the AI is listening for individual words and trying to figure out whether I'm saying spoon, swoon, swoon, whatever, based on just that word instead of like the larger context, do most of them just use that smaller context, or do they take in more?
Yeah, they do. They start with a smaller context. It always starts with a very small context, but then they sort of like build. And that's what happens as part of like hidden Markov models, Gaussian mixture models as well. So they do go back, and I wish that I had that up and running. So they will go by individual phoneme and add different phonemes together to like form a word. But they do go back, like, does that make sense? And then you get to the language model, and does it make sense for these two words to be together? If it doesn't, because you have how confident the algorithm is. So let's say that you have, I spoon-fed my baby. Right, so you end up with the sentence. I don't think it really makes sense, but let's say you end up with that sentence. It will go back because that spun, it's not gonna have, like 95% confidence that that's the right word. And so anytime there's like issues around, every time you're not at a certain percentage, it will go back and sort of like check what was the other option, and does that make more sense as part of like a full sentence. But it does start individually because again, you're going through it like letter by letter almost, not letter by letter, but like phoneme by phoneme to start with. Yeah.
So if you combine dialect with accent, right, like that infinitely makes it
right.
Okay.
And so the acoustic model that we talked about, the one that is most widely used, the TIMIT, we're talking about 8 different dialects of the English language in the US. Are there more dialects in the English language than 8? Yes. So is that gonna have everything? It doesn't. And so that's one of the issues, is that we are using these acoustic models that don't necessarily like provide enough dialects to really be able to match those specific like phonemes and then words and then phrases together.
Yeah. It should go the other way around, because as a person, I'm not listening to the individual.
Yeah.
I'm listening to the whole sentence.
Right, but you need to try to figure out what the sentence might be first, because it's a computer. It doesn't actually know what the full sentence is until it puts together like, these are the possibilities for this word. These are the possibilities for this sentence. Which one makes more sense?
And accent helped me define where you're trying to go, because as you said it, if you were speaking standard American English or AAVE, like the way that you arrange those words is different.
Yeah.
And therefore, what I think you're trying to get to.
Right, exactly. Yeah, yeah. That is the problem. Exactly. It's still really impressive. Speech recognition has come a long way in the last 20 years. The fact that like we even have something like this is really cool. I do have speech recognition for like most of my classes, and it works fairly well for me, but then I have like students giving presentations, you know, at the end of the quarter, and it like doesn't always work super well. We do have a lot further to go, and you know, that's again, it's easy to make software for kind of like the best case, but then you know, like there's other cases too, and that's where that a lot of work still needs to happen.
Just quickly on the text-to-speech on the other way around, is there software for that as well? Because it sounded like an extremely manual process to add all of those things.
Yeah. I mean, yeah, absolutely. So if you were to use something like Dialogflow, most of that happens. Dialogflow does most of that. So it is able to like figure out most of those things. Obviously, you know, in terms of prosody, that's something that you might still want to like make changes to, and you can go into the SSML and update that. Yeah, but yeah, the text normalization, the phoneme pronunciation, yeah.
Okay, so Dialogflow talks back to the user.
Yeah, it does both. So you talk to it, and then, I mean, it's sort of, you can use it as a messenger, but you can also talk to it and it talks back. And the Dialogflow agent is something that you can add within a Google action, and it's basically like most of the work.